Welcome to the third class of our course. I am Gabrielle Nornberg, and in this class we are going to talk about a priori bounds and blow-ups for our dynamical system. We are going to see that trajectories which are defined for all time, they live inside this box here. And the two ways of escaping that box is either having a blow-up backward in time in z, or having a blow-up forward in time in x. And we're going to see that these blow-ups occur at finite time. More precisely, if a trajectory is defined for all forward time, then it needs to be bounded in x. While if it's defined for all forward time, it needs to be bounded in z. And let us prove this first statement. And let us consider a trajectory which is defined for all forward time and assume by contradiction that we crosses that line x equals to n tilde minus 2. Let us consider here the operator n plus, for instance. So if the trajectory crosses that line, let us say at some point t1, then since the vector field is well defined at that line, in the sense that it always points down and to the right, it means that in particular x always increases from that value and z decreases. In particular, we have that x needs to go to infinite as this goes to infinite. Why? Because since z only decreases, if we had x as a bounded trajectory, then by the Poincare-Bendixson theorem, the trajectory would need to converge either to a fixed point or a periodic orbit. But neither of them exists on the right of this plane. So x needs to go to infinite. In this way, if it goes to infinity, we can take a point, t2, which is larger than n minus 2 as well. Recall that for n plus, we have this ordering. N is larger or equal than n plus tilde. Okay? And then, why this appears? Because we had a dynamical system which is piecewisely defined in each of these regions. We have a system in the region R plus and another one in the region R minus. So if such trajectory reaches the region R minus, then at some point, let us say at some point t3, it means that since z is decreasing from this point on, then we will remain in this region R minus here forever. Then from this point t3 on, we can use just the second definition of the equation for x, rewrite this equation in this form, correctly write this as a differential function in t, integrate from t3 to t, and rearrange the terms and obtain that x needs to blow up at finite time. And this contradicts the assumption that we had a trajectory defined for all time. In the same way, if the trajectory is stayed in the region R plus forever, we can argue by performing the same integration, arguing with the equation in the region R plus. And this we prove. Now the bound for z. This is even simpler because if we have a blow-up of that point that we are going to prove that this gives a blow-up in finite time, if we have a trajectory that crosses that line z equals to lambda n plus a, at some point, let us say some point t1 in the first quadrant, then it means that for all t less than t1, the coordinate z of that trajectory is larger than this number. So in particular, it stays above the line L plus of concavity, and so it remains in the region R plus. With this, we can use only the first equation, and again, rewriting and integrating, we obtain again that this blow-up, which occurs in backward time, is finite, is at finite time. So, what about the blow-ups in the third quadrant? In the third quadrant, we always have these blow-ups occurring for any trajectories. Why? Because here the flow is always pointing down and to the right. In each point we have this flow, which can be seen very easily from the equations. And in the same way, we see that at such blow-ups, at such extremities, then we have blow-up in finite time, in the same way as we did before in the first quadrant. We can also classify all the blow-ups which occur in the first quadrant in the following way. By a blow-up in Z in the first quadrant, what happens with the corresponding solution of our second order PD problem? In this case, recall that U prime and U cannot vanish at the same time. Why? Because we have the uniqueness of the second order ODE problem, and we have a nonlinearity which is Lipschitz continuous, so then we cannot have at the same point for a non-trivial solution a function vanishing also in U and vanishing with its derivative at this point. So, in a point where Z blows up in the first quadrant, it means that this goes to plus infinity. This is equivalent to say that U prime is converging to zero at that point. And if U prime is converging to zero, X in turn is converging to zero as well. So a blow up in Z in the first quadrant is equivalent to say that the first derivative is vanishing and X is converging to zero. So we have a well-defined asymptote for that blow up. In the same way, a blow up for X, let us say a blow up here in X, when X goes to plus infinity in the first quadrant, means that U in this case goes to zero, and with that, since U and U prime cannot vanish at the same time, this goes to zero as well. So this blow up in X in the first quadrant is characterized by the vanishing of the function U and also Z. Okay, this gives us a complete picture of the admissible blow-ups in the first quadrant. No other blow-ups exists in that quadrant. And let us only point out that such blow-ups only occur at finite time, because you remember that solutions which are defined forward or backward in time, they always will be bounded at some in some component X or Z. So the only way of having a blow up is at finite time. As a first application of that characterization in the first quadrant, we obtain that trajectories which start in the region R plus need to have a concavity change for their corresponding functions of the second order PD at least once. This means that for a trajectory, for instance, the regular trajectory or a trajectory which blows up backward in time, both of them need to cross the concavity line at least once. Why? This is just because a blow-up like this is not admissible, because we have already characterized all the blow-ups admissible for our system. And continue, we can also characterize in the same way the blow-ups in the third quadrant. Recall that the trajectories, the vector field is always points to the right and down. And when we have a blow-up in z, in this case, when z goes to minus infinity, this means that u prime needs to converge to 0 at that point, and with that, x needs to go to 0 at the same point. And in the same way, we can characterize such blow-ups in x. When x goes to minus infinity, we have that u vanishes, and in this case, z needs to vanish as well. And this gives us a complete characterization of blow-ups and asymptotes that occur in the third and also in the first quadrant. With that, I finish. I thank your attention and see you in the next class.